Okay, so this question is all about mechanism. Can you spot how this starting alcohol rearranges to give a new bicyclic product that has captured methanol somehow? So key points are that we're doing this with acid. We have a methoxy group in the product, and we're using methanol. And we've gone from a 6-6 system, so you don't really need to know the terms, but that's an oxidecalin system, to a 7-5 ring system. Now, to go from one ring size to another, this really is sort of pointing towards a rearrangement. Acid is involved with an alcohol. We know that we can form carbocations under those kind of conditions. We know that if we form a carbocation, it can rearrange. We know the rearrangement can lead to changes in ring sizes. And we know that carbocations can be captured by nucleophiles like methanol. So it all points towards generation of a carbocation that rearranges and gets trapped by methanol. Now, one of the tricks to this question is going to be spotting how do we get from one bicyclic ring system to the other. And this can get a little bit confusing because, you know, what's bonded to what. So I really recommend starting off by numbering your ring system. And it doesn't matter how you do it, because you just want to look for consistency between one molecule and the next. Okay, so I might not draw those numbers on every structure, but we'll come back to that. So the first thing in this mechanism is to spot that the alcohol is going to have to be protonated to make it into a good leaving group and therefore generate a carbocation. So the first step is going to be making that into a good leaving group. Okay, so now we've got one of our favorite leaving groups in organic chemistry, a protonated alcohol. And it's one of our favorite leaving groups because water is such a stable molecule. It's a great leaving group. So it will depart, leaving behind a carbocation. Okay, so if that bond breaks, we're going to get a carbocation left behind and water is the leaving group. So we can draw out minus water, and made a mistake there. We've got a methyl group there, make sure that's there. I won't put the numbers in yet, that'll become important once we rearrange. There's that methyl group, here's our other 6-membered ring, and there's our carbocation. So we might remind ourselves that it's a secondary carbocation, and therefore it's really prime material for doing a rearrangement. So now we might put those numbers back in again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I guess there's a little bit of a leap here. We need to know what group migrates to get to the product. It's pretty safe to assume that that oxygen and that ring is what start off in the oxygen of the ring in the starting material. It's also not too much of a leap to say that number 10 carbon has a methyl group in the starting material, and it's the carbon next to that oxygen has a methyl group in the product as well. So really, it seems likely that the number 10 carbon has not done anything funny. It's still there and still has its methyl group attached. So this really sort of points to the fact that the methyl group is unlikely to be migrating. It's not going to lead us to the product if we make that methyl group migrate. We know the methyl groups aren't the best at migrating if there's other choices, and so we might want to look for other possibilities. So what happens if I keep on numbering around the system? So if I go 2, 3, 4, 5, 6, 7, 8, 9. So in this starting material, we've got the 5 and the 10 carbons are bonded together, and in the product we've got, it looks like the 5 and the 9 carbons are bonded together. So could it be that the 5 carbon and its pair of electrons have migrated across to the 9 carbon? Well, if we look at the carbocation we formed, it's at that 9 carbon. So that really does look good. So let's get that bond with its pair of electrons and migrate it across to that position there. I think one of the keys here is don't try and draw it out in the aesthetically pleasing manner that it's drawn in the final product. Draw it out as it is in that carbocation, and then draw it out again in a more sort of pretty looking structure. So let's draw. I'll go back to my blue coloring. Now this is a very common mistake, and I think it's good to have a pencil if you're doing this in an exam situation. I drew a bond in there briefly that had migrated, so I'm going to have to delete that. Okay, I'll put my numbers in. I'll just get that number out of the way actually. 9 there, and 10. And we have a methyl group attached to 10. There's that methyl group. Okay, so we've got, with that migration, 5 with its pair of electrons has migrated to be bonded to 9. So that bond is migrated to the between 5 and 9 like that. Now, a really common mistake in going through these mechanisms is to put the charge, the positive charge, in the wrong position. So what we've done is, if we look at this, and I'll get another color, we've taken electrons away from carbon 10, from the 5-10 bond, away from carbon 10 and push them towards 9. 5 still has a bond, it's just migrated who it's bonded to. So the atom that has the positive charge left behind is going to be the number 10 position, that one there. Okay, now in these questions, it's a really good idea, and you may explicitly be asked in an exam situation to draw out all resonance forms for structures that are resonance stabilized. And this one is a real classic example of that. A positive charge next to a heteroatom, particularly oxygen and nitrogen, can be really greatly stabilized by that heteroatom because it has lone pairs of electrons. So we can draw a resonance form where that pair of electrons moves in. We can draw another resonance form of this carbocation. Okay, I'm going to draw it out in that ugly way again still. Okay, and I'm not going to bother with the numbers this time, but I've got a double bond there, and this is really ugly looking bond angles, but we'll just have to put up with it for now. And there's our positive charge because we've taken a lone pair of electrons on the oxygen and we've moved them to be shared in a bond with that carbon. So now it has a formal positive charge. And then we've got that bond there between the 5 and the 9 positions. Okay, so there's our other resonance form. And for full marks in an exam situation, you're really normally going to be expected to draw resonance structures for things like this that are resonance stabilized. So that is a very special type of carbocation. So you might see it called an oxonium ion or an oxocarbenium ion, and they're much more stable than just an ordinary carbocation. Okay, so let's draw that out in a more sort of aesthetically pleasing manner. And you can use your numbers again. So we've got the numbers on the previous thing. We can also look at the structure of the product and use that as a guide. So we've got a 5-membered ring is, I'll get back to my blue color. 5-membered ring is pretty easy to draw, and then I struggle with 7-membered rings. I struggle to get them looking nice, that's for sure. There's a 7-membered ring, and let's do those numbers just to make sure we've got everything in the right place. So we have an oxygen. Whoops. Put that in blue. Okay, at that position there. And we're starting with oxygen as 1 and going around the ring like this. Okay, that 10 position has a methyl group. and we showed it as a oxocarbenium ion. Okay, so we're almost at the product now. We've just got to capture this carbocation with methanol and then lose a proton. So let's get our methanol and show it trapping that carbocation. And if we don't show another curly arrow, we're going to have a 5-coordinate carbon, pentavalent carbon, no good. So we're going to have to break that weak pi bond and push electrons toward the oxygen. Sometimes people like to talk about an electron sink. So there's something that's pulling electron density towards it, or where electrons end up at the end of your curly arrow cascade. That oxygen has a positive charge because it's sharing its pair of electrons with the carbon next to it and a pi bond. We push electrons back onto it, it's just getting its lone pair back and neutralizing that formal positive charge. Okay, so we're going to draw this 5-7 ring system again. I was going to go to blue, so let's go back to blue. Okay, we've got our oxygen there. It has both its lone pairs of electrons back now. It's neutral. We've got the methyl group, and we've got the methanol that's been added. Now, this oxygen here had its full pair of electrons, and now it's sharing that with the carbon and still has its remaining 2 substituents, so it has a formal positive charge. Okay, and I think that's everything. I won't bother putting the numbers in because all we need to do now is lose that proton. And you can either just draw -H+, most lecturers, professors are going to be happy with that, or if you really need to show every curly arrow, then you can show that bond breaking. And normally for proton transfers, that's being transferred to something. So for example, it could be the conjugate base associated with the acid that we used, or it could be anything pretty much with a lone pair of electrons. This is a high energy species, so just having a transfer to methanol, that could be one way of showing it. The important thing is that we need to lose a proton to get to the final product. Okay, so there's a few components that mechanism. We need to spot that a carbocation is likely to be involved. There's a rearrangement that changes the ring size. The rearrangement happens by migration of a particular CC bond, and that'll give us the new 7-5 ring system. And that a really special thing about the carbocation that we form is that it's stabilized via being the carbon with a positive charge being next to an oxygen with a lone pair of electrons that can stabilize that positive charge. And to get full marks for this type of question, you would normally be expected to draw in that resonance form of the carbocation as well as the one that you would normally draw for a carbocation. Okay, so I hope that helped you with this style of carbocation rearrangement question.